Hi students, today topic is temperature dependence of resistivity. Resistivity of certain material, how it depends upon temperature. When temperature changes, how resistivity of conductor changes. For example, in case of metals, if you will change the temperature, then what happens to the resistivity? If in case of semiconductors, if you will increase the temperature, then what happens? In case of insulators, what happens? With the change in temperature, how the resistivity of different materials changes, that we are going to discuss. We know already that the resistivity depends upon temperature. On some factors the resistivity depends, that is resistivity depends upon nature of material and resistivity depends upon temperature. These are the factors on which the resistivity depends. What is resistivity? Resistance per unit length and per unit area is called as resistance per unit length per unit area. You take the 1 meter length, okay, 1 meter square area of cross section, okay, anything, 1 centimeter length, 1 centimeter square area of cross section, unit length, unit area of cross section. Then for that some resistance is there, that resistance is called as resistivity of certain material. Resistance per unit length per unit area is called as resistivity, and we know formula for the resistivity, right? Okay, we already discussed that one. Now for example, the change in resistivity of a material, on what factors it will depends, let us see. And for example, this is considered as rho naught. Rho naught is the resistivity rho naught is the resistivity of material at T naught degrees Celsius, right? At T naught degrees Celsius. And the rho T is the rho suffix T, right? Rho suffix T. This is rho suffix 0, rho naught, resistivity at T naught degrees Celsius. And rho T is the resistivity at resistivity of material at T degrees Celsius, okay, at T degrees Celsius. And now this change in resistivity, when the temperature changes from T naught to T, then how resistivity changes? It changes from rho naught to rho T. At temperature T naught, the resistivity rho naught. At temperature T, the resistivity is rho T. Okay. And now the change in resistivity, that is the change in resistivity depends upon some factors. The change in resistivity directly proportional to the change in temperature. If the change in temperature is more, then the change in resistivity also more. Okay. And this we can write like this: the change in resistivity is rho T minus rho naught. This is proportional to the change in temperature, that is T minus T naught. This is equation 1. And the change in resistivity is also depends upon one more factor, that is the change in resistivity depends upon initial resistivity, right? Change in resistivity depends upon initial resistivity. Initial means starting resistivity, right? Okay, at T naught degrees Celsius. And this we can write, the change in resistivity is rho T minus rho naught, rho suffix T minus rho suffix T naught. This is directly proportional to initial resistivity. Rho T minus rho naught, the change in resistivity directly proportional to the initial resistivity. Then what is initial resistivity? Initial resistivity is rho naught. Okay, when we combine these two from equation 1 and 2, we write like this, that is the change in resistivity proportional to the initial resistivity into change in temperature. When the proportionality is removed, we will get a constant, that is alpha rho naught into T minus T naught. Okay, this is the change in resistivity formula, where alpha is called as temperature coefficient of resistivity. Temperature coefficient of resistivity. This is the alpha. And now from this alpha formula we can also write, right? The alpha formula is we write the alpha formula. What is the alpha formula from this equation? Right, now this from this we write temperature coefficient of resistivity, this is equation 3, and alpha we write as rho t minus rho naught by rho naught into t minus t naught. This is the formula for alpha. Okay, and now here unit is, okay, SI unit of alpha. SI unit of alpha is per degree Celsius. Okay, per degree Celsius or per Kelvin we write. Okay, unit of resistivity per degree Celsius or per Kelvin also we can write. Change in temperature in degree Celsius equal to change in temperature in Kelvin, per Kelvin or per degree Celsius we write. Okay, and now let us see resistivity at T degree Celsius. If you want resistivity at T degree Celsius, I want, that is rho T is rho T. Then this rho T formula from equation 3 we write. This is equation 4. From equation 3 we can write that one. Okay, and how we write the rho T formula from that? We take minus rho naught to right side, then we will get rho naught plus alpha rho naught into t minus t naught we write. This rho T is equal, rho suffix 0 is common, rho naught is common, 1 plus alpha into t minus t naught we will get. This is resistivity at T degree Celsius formula. Okay, and now how resistivity depends upon temperature? Alpha may be, okay, alpha may be, alpha is what? Temperature coefficient of resistivity, right? Temperature coefficient of resistivity, temperature coefficient of resistivity. How to define this? Okay, can you tell? Temperature coefficient of resistivity, right? And for that we take the rho naught as 1 unit, okay, and t minus t naught as 1 unit. At that moment the alpha is equal to what from equation 3? From equation 3, okay, from equation 3, not 3, from 4, okay, from equation 4 we write alpha is equal to, what we write? Rho T minus rho naught we write. Means change in resistivity per unit change in temperature and per unit initial resistivity is called as alpha, temperature coefficient of resistivity. Change in resistivity per unit change in temperature and per unit initial resistivity. The change in resistivity, the change in resistivity per unit initial resistivity, per unit initial resistivity, per unit initial resistivity, and per unit, okay, or per unit or 1 degree Celsius, per 1 degree Celsius change in temperature, change in temperature is called as what? Temperature coefficient of resistivity is called as temperature coefficient of resistivity, temperature coefficient of resistivity. Okay, right, and this is definition of alpha. And I will tell one more formula in terms of temperature coefficient of resistance also it will be there, temperature coefficient of resistance. Then in the note you can write that point, note, that is temperature coefficient of resistivity is alpha, temperature coefficient of resistance we write, temperature coefficient of resistance or resistivity Okay, that formula we can also write in terms of resistance also. RT minus R naught by R naught into, we write T minus T naught. T minus T naught. Okay, same formula. Instead of resistivities, we can write resistance. From this RT formula also we can write R naught of 1 plus alpha into T minus T naught. Exactly same as equation 5 and equation 4. What is the difference? In equation 4 and 5 we are using the resistivity terms rho, rho, rho. Here also rho we are using. But in this, instead of resistivities, here we have the resistance. What is RT at here? This is the resistance. Resistance at what temperature? T degrees Celsius. What is R0? That is resistance at T naught degrees Celsius. Okay? And what is alpha at here? Alpha is the temperature coefficient of resistance. In terms of resistivity, if you write, alpha is called as temperature coefficient of resistivity, and in case of in terms of resistances, if you write, then alpha is called as temperature coefficient of resistance. Then on let us see, alpha may be positive, negative, or it may be 0 also, nearly 0 also. Okay, now I will tell alpha value. Okay, alpha value, this is the first point. The second point I am going to tell, alpha may be positive or negative or nearly equal to 0. Okay, right. And now take the screenshot and note all the points. And now I am going to explain how the resistivity varies for the metals, conductors, semiconductors and insulators and alloys, right? And it was very simple, and you listen very carefully. Now I am going to rub the board, and then after that I will continue. Okay? Okay, first conductors. How the resistivity of conductors and the resistance of conductors varies with the temperature, that I am going to explain. For that, okay, in case of conductors, in case of metals, okay, metal conductors, in case of metal conductors, alpha is positive. Okay, alpha is positive. And now conductors, how the resistivity varies? Resistivity formula is m by n e square tau. This we derived in lecture number 3.2, drift velocity concept. Okay, this we derived in the lecture number 3.2. Refer 3.2 lecture. Okay, refer 3.2 lecture. In that its derivation is there. Okay, and now this is the m is mass of electron, it's constant. M is mass of electron. E is charge of electron, that's also constant. And n is the number density. What is number density? Number density means number of electrons per unit volume. Number of electrons per unit volume. Number of electrons per unit volume. Okay, number of electrons per unit volume. What is tau in this? Tau is the relaxation time. What is relaxation time? In this also you have to refer the 3.2 lecture. That is the average time interval between the successive collisions. For example, electron is moving like this. Here the electron is collided with some ion, and now the electron is traveling like this, traveling, and here again the electron is collided with some other ion. From here to here there is no collision. That means Now the electron travel from here to here relaxedly without any collision, and the time in which the electron travel relaxedly without any collision or the time interval between the successive collisions of electrons with the positive ion. Here electron is collided with the positive ion. For example, electrons are moving in the conductor. Free electrons are there means positive ions also there, because electrons are generated from the atoms. For example, any atom, copper atom, if it loses one electron, this is the free electron, this will become positive ion. Like this, if in the copper metal, electrons are there along with the copper ions are there. When the electrons are moves, they will collide with the copper ions. Now here electron is collided with the copper ion, then after going to certain distance, again the electron is collided with the positive copper ion. This is the time interval, okay, between the successive collisions of electrons with the positive ions. And now here this time, okay, is called as relaxation time. Here electron collided with the electron is going, and here electron collided with the positive ion. Next collision where occurs? Here occurred, right? From here to here there is no collision. Electron freely traveled, relaxedly traveled without any collision. That time, the time in interval between, or the time gap between two successive collisions. Here the electron collided with the positive ion, here electron collided with the positive ion. In between these two positions, right, the time is said to be, the time interval between successive collisions of electrons with the positive ions is called as relaxation time, that already we discussed. And what happens in this case? In case of metal, there are fixed n value is there, number of electrons per unit volume, and all are constant. Okay, in case of metal, okay, and m, n, e almost constant. Okay, then how resistivity depends upon the relaxation time? Resistivity inversely proportional to the relaxation time, right? And that means in case of metals, if temperature increases, when temperature increases, electrons goes randomly, then more collisions will take place. That means relaxation time will be decreases. In case of metals, if temperature increases, then the number of collisions increases. When number of collisions increases, relaxation time decreases. Okay, now we can write. In case of metals, okay, if temperature increases, then what happens? Relaxation time decreases. Why relaxation time decreases? When temperature increases, electrons goes randomly and collisions will increases. When collisions increases, then the relaxation time is decreases. Relaxation time decreases, hence resistivity increases. Remember that. Okay, in case of metals, what happens? If temperature increases, then what happens? Resistivity and resistance, these two are increases. Okay, if temperature decreases, resistivity and resistance two are decreases. This is how resistivity depends upon temperature in case of metals. Let us draw one graph for this. Okay, and the graph and resistivity versus temperature graph, and the rho t graph we write. Resistivity versus temperature graph, rho t graph. How we will get that graph? Let us see. Resistivity increases with increase in temperature, right? Then we will get the graph like this. This is the resistivity versus temperature. Okay, and now let us go for another one. How the resistivity varies for the semiconductors and insulators. Semiconductors and insulators. In case of semiconductors and insulators, alpha is negative. Okay. In case of semiconductors and insulators, alpha is negative. Okay. And now alpha means what? Temperature coefficient of resistivity or resistance. Alpha is negative. In case of semiconductors or insulators, alpha is negative. And now for semiconductors or insulators, actually free electron availability is very less in the semiconductors and insulators. Semiconductors example is germanium, silicon are the semiconductors. Sometimes they will act as a conductor, sometimes they will act as a insulator. And this is insulator. In insulator semiconductors, there are no free electrons. But when the temperature is increases, then the free electron density will increases. There is a chance to increase the free electron density. Okay, right. In case of semiconductors, if the temperature increases, then the covalent bonds will breaks, and due to that some free electrons will generate. Then number density will increases, right? In case of semiconductors, here we have the formula for the resistivity, m by n e square tau. Here almost all are constant. Here in case of this one, we take the resistivity inversely proportional to the number density. Okay. And now when temperature increases, in case of semiconductors or insulators, in case of semiconductors and insulators, if temperature increases, then what happens? Covalent bonds will break, some free electrons availability increases more, right? Then n is, in case of semiconductors and insulators, if temperature increases, then number density means number of electrons, free electrons per unit volume, number density increases. Okay. Hence resistivity decreases. When number density increases, resistivity decreases. Here in case of metals, relaxation time decreases, resistivity increases. In case of semiconductors and insulators, if temperature increases, then the number density increases. Hence resistivity, n increases means resistivity. What happens to the resistivity? Tell me. Resistivity decreases, right? And here we write, if temperature increases, then what happens? Resistivity decreases. Resistivity comma resistance decreases. If temperature decreases, okay, and resistivity and resistance increases. This is opposite nature. Here in case of metals, if temperature increases, resistance increases, resistivity increases. In case of metals, if temperature decreases, resistance and resistivity decreases. But in case of semiconductors and insulators, if temperature increases, resistivity and resistance decreases. Opposite behavior will be there. When the temperature increases, resistivity and resistance decreases. For this, if we draw the graph, then how it will be there. And you take the screenshot and note the points in the notes. Now I want the rho T graph for the semiconductors and insulators. Rho T graph, resistivity and temperature graph. For what? resistivity temperature graph. Resistivity temperature means rho T, right? Rho versus T graph for semiconductors or insulators, right? Semiconductors or insulators, how it will be there, right? In this what happens here, this is for what? This is for metals, means conductors. In case of conductors, what happening, the graph is going up, means when temperature increases, when you go to right side, temperature increases, resistivity also increases. That is for conductors. But we are discussing the semiconductors and insulators. In this case, resistivity decreases with increase in temperature, right? Then this is the resistivity is taken on y-axis. Resistivity denoted with rho. This is not P. Okay, right. And now resistivity denoted with the rho. And now we have to draw the graph. Temperature increases. When temperature increases, what happens for the semiconductors? Resistivity and resistance decreases, right? Because of increase in number density. More electrons will increases. More electrons produces more current. More current means resistivity decreases, right? And the graph we will get like this. Okay, this is the graph. And this is for what? This is for semiconductors. Semiconductors or insulators, right? Semiconductors or insulators graph. And now the next one is alloys. How resistivity depends upon temperature for the alloys. Do you know alloy? Alloy means it is a mixture of 2-3 metals, right? Now we will go for the alloys. And in case of alloys, how resistivity depends upon temperature. Okay, now nichrome, we will take nichrome. Nichrome is the combination of nickel, right, iron, and what, tell me, do you know? Nichrome, nickel, iron and chromium. Okay, and nichrome is the alloy of nickel, iron and chromium. It was very easy to remember. NiC, nickel, N is the nickel, I is the iron, C is the chromium. Remaining is chromium. And now this nichrome is an alloy of nickel, iron and chromium. And for this alloy, how the resistance depends upon temperature, how resistivity depends upon temperature, that we are going to discuss. In case of nichrome, right, alpha, right, it's an alloy. For alloys, alpha is nearly 0, right? Negligible. Let us see. In case of alloys, what happens? There is no resistivity is almost independent of temperature. Okay, this alloys, that's why this is this nichrome or otherwise manganese or some other are there. They are constant and they are useful to make the standard resistors, and they have the high resistivity and they have the least temperature coefficient. Alpha is very less. Okay, nearly 0. Alpha is very less. And now that's why they are used to make the standard resistors. Okay, manganese wire is used to make the standard resistors like rheostats or some other, right? And for the alloys, how the resistivity depends? Resistivity of alloys almost independent of temperature. The variation of resistivity of alloys with increase in temperature or with change in temperature is neglected. Okay, is neglected, and resistivity is almost independent of alloys. Resistivity is independent of temperature, and alpha is nearly 0. Okay, alpha is nearly 0 means alpha formula is what? Rho t minus rho naught by rho naught into t minus t naught. When alpha is nearly 0, then the change in resistivity also nearly 0 means no change in resistivity. Okay. Alloys have high resistivity and low temperature coefficient. Of resistivity. Hence, they are used to make the standard resistors. Okay, standard resistors. Standard means fixed resistors, right? Fixed resistance. Okay, manganese or constantan are used to make standard resistor means it has fixed resistance. Its resistance does not changes with the temperature, right? In case of alloys, resistance does not depends upon the temperature. And now let us see, we will draw the graph for the alloys. How the resistivity varies upon changes with the temperature. Let us see. Resistivity rho T graph. Resistivity temperature graph for what? Rho T graph for alloys. Okay. And now the graph we will get like this. For example, this is 1 ohm meter and this is 1.2 ohm meter. The graph we will get like this. This is the variation of resistivity. Almost straight line we will get. Little change will be there, little increase will be there. This is the resistivity on y-axis and the temperature is on x-axis. When the temperature increases by large amount, but the resistivity changes from 1 to 1.2, it is very less, right? It not rises by large amount, and the graph we will get like this. Okay, almost straight line, but little bit resistivity increases. It is going up, but not much up, right? And when the resistivity changes, temperature changes from here to here, but the resistivity is slightly goes up. Means increase in resistivity is negligible. Okay, and now this is how resistivity depends upon temperature in case of conductors, semiconductors and alloys. In case of conductors, resistivity increases with increase in temperature. In case of semiconductors, resistivity decreases with increase in temperature. Opposite behavior will be there. In case of alloys, resistivity does not depends upon temperature. Almost the resistivity is constant. It does not depends upon the temperature. Okay, metals, resistivity increases with increase in temperature. Conductors, resistivity increases with increase in temperature. Insulators or semiconductors, resistivity decreases with increase in temperature. And in case of alloys, resistivity does not depends upon the temperature. And let us see. I am going to explain one more point. that is the note you wrote. Okay, we have the resistance R0 is the, for example, the resistance at 0 degree Celsius. Okay, and R100 is the resistance at 100 degree Celsius. Resistance at 100 degree Celsius, and RT is the resistance at T degree Celsius. At T degree Celsius. Okay. For example, alpha is the temperature coefficient of resistivity. Alpha is the temperature coefficient of resistance. Temperature coefficient of resistance. Then we have to derive the formula for the temperature T in terms of RT, R0, R100. I will derive. Okay. We know formula resistance at T degree Celsius, right? We know RT is equal to R0 of resistance at T degree Celsius. RT is equal to resistance at T0 degree Celsius into 1 plus alpha into T minus T0. This you know already. RT formula you know, that is R0 into 1 plus alpha into T minus T0. This formula is already you know. Okay, RT, okay, R0. Here, first according to that formula, what we write the R0, R100 formula, or RT formula, what we write? Resistance at T degree Celsius. R0 is the resistance at 0 degree Celsius here. Now, what happens? First we will take like this. Okay, the temperature rises from 0 degree Celsius to 100 degree Celsius. At that moment resistance rises from where to where? Resistance rises from R0 to R100, right? In this case, what we write we have formula in previously. Okay, when temperature changes from T0 to T, the resistivity changes from, resistance changes from R0 to RT. RT formula is R0 of 1 plus alpha into T minus T0. Here T0 is initial temperature. At T0, R0 is the resistance at T0 temperature. But here R0 is the resistance. R0 is the resistance at 0 degree Celsius. R100 is the resistance at 100 degree Celsius. We write here in place of T, we write R100. Okay. R0 is the resistance at 0 degree Celsius. R0. Okay, into final temperature here R100, initial resistance is R0, final resistance is RT. Okay, R0 to RT, initial temperature T0, final temperature is T, and here initial temperature is 0, final temperature, this is T0, this is T, this is R0, and this is RT, right? Similar to that we have to write. And here R100, temperature changes from 0 degree Celsius to 100 degree Celsius, and temperature changes from 0 degree Celsius to 100 degree Celsius. First I will write one formula. When temperature changes from T to T0 to T, the resistivity changes, resistance changes from R0 to RT, then RT formula is what? R0 into 1 plus alpha into T minus T0. Okay, this is equation we already know, previously we derived. And here the temperature is changing from 0 degree Celsius to T degree Celsius. The resistance at 0 degree Celsius is R0, and resistance at T degree Celsius is R suffix T. Then this formula we will write as, what do we write the formula? RT, capital T becomes small t, R capital T become R small t. Then R small t is equal, R0 is R0 only, right? Okay, 1 plus alpha into T minus T0. Here T minus T0, change in temperature, but here the change in temperature is small t minus 0. Okay, then what you will get here? RT is equal, we will get as R0 into 1 plus alpha t we will get. Okay, and this we will write like this, and you can multiply RT is equal, we will get as R naught plus R naught into alpha T, we write. We take R naught to left side, then RT minus R naught is equal to R naught into alpha T, we write. This is equation 1. Okay, now the next initially temperature changing from 0 to T. Next I am considering that the temperature is changing from 0 degrees Celsius to 100 degrees Celsius. The resistivity changes from, resistance changes from, at 0 degrees Celsius resistance is R naught, we are considering already, right? And at 100 degrees Celsius the resistance is R100. Then what is the formula, how it will changes? T naught to T, R naught to RT. Here RT become R100. R100 is equal to, okay, R naught here, here also R naught. Final resistance is equal to initial resistance into 1 plus alpha into change in temperature. Final resistance is R100 is equal to initial resistance is R naught into 1 plus alpha into change in temperature, T minus T naught, but the change in temperature is 100 minus 0.8 here. Okay, this we write as R100 is equal to R naught plus R naught into alpha 100, we write. Okay, this R naught like on the left side, R100 minus R naught is equal to R naught into alpha 100. This is equation 2. Now we can divide these two equations. Equation 2 by equation 1 we have to do. Then R100 minus R naught by, or equation 1 by equation 2 we will do. We want to find out the T. Equation 1 by equation 2. What you will get? RT minus R naught by R100 minus R naught is equal to, right side, left side we have to divide RT minus R naught by R100 minus R naught. Right side is what? R naught alpha T by R naught alpha 100. This R naught alpha will cancel. Okay, this will cancel. Then what you will get? Answer. The answer we will get is okay, can you tell? The next equation we will get like this, RT minus R naught by R100 minus R naught is equal to T by 100, right? I want the T formula. T formula is RT minus R naught by R100 minus R naught into 100, right? This is the formula that is used to find out the temperature. Okay, you know R naught resistance at 0 degrees Celsius. You know R100, that is resistance at 100 degrees Celsius. Okay, now you want to find out at what temperature the resistance is RT. Okay, RT is resistance at what? Resistance at T degrees Celsius. This T I want to find out. Okay, for that the formula is that one. Okay, the temperature at which the resistance is RT, R suffix T. R naught is the resistance at 0 degrees Celsius, R100 is the resistance at 100 degrees Celsius, RT is the resistance at T degrees Celsius. Okay, for example, we have one copper. Okay, for the copper the resistance at 0 degrees Celsius 2 ohm, and the resistance at 100 degrees Celsius is 50 ohm. And for example, they are asking at what temperature the resistance is 5 ohm. This is the question. We can use this formula, right? Look at here. At 0 degrees Celsius the copper resistance they give. At 100 degrees Celsius they gave the resistance. Okay. And now at what temperature the resistance is 5 ohm. This T we have to find out. RT they gave, R0 they gave, R100 they gave. This is interesting formula. Okay, I will tell this formula derivation. First, the temperature changes from 0 to T. The resistance changes from R0 to RT. Then RT final temperature equal to initial temperature R0 into 1 plus alpha into change in temperature T minus 0. From this R0 is multiplied, then we will get this formula. From this R0 taken to left side, then RT minus R0 we will get this one. And then after that, if the temperature changes from 0 to 100, the resistance changes from R0 to R100. At 0 degree Celsius, resistance is R0, at 100 R100. Then final resistance R100 equal to initial resistance into 1 plus alpha into change in temperature. Change in temperature is 100 minus 0. Then again we have to find out the R100 minus R0. Then we have to divide them. Then we will get the final formula. Okay, I will give one homework problem based on this formula. Then we will close today's lecture. Okay, this is our question. The resistance of the platinum wire. Okay, the resistance of the platinum wire of platinum resistance. Actually, thermometers also made with the resistance. They can use it to measure the temperature. Thermometer is used to measure the temperature. When temperature changes, resistance also changes. Based on the change in resistance, they can measure the temperature because resistance depends upon the temperature. Then how much resistance it is changed with the temperature we can calculate. By that we can also calculate the change in temperature and temperature. That are the resistance thermometer. That means thermometer is a device used to measure the temperature, but it can be measured based on the resistance. Look at here, the resistance of platinum wire. Okay, in the resistance thermometer platinum wire is used. It is a resistance wire. Okay, and that resistance, when the thermometer is inserted in the ice point means at 0 degree Celsius. Okay, at 0 degree Celsius, ice point means 0 degree Celsius. The resistance value they give, okay, how much it is noted, that is 5 ohm. And the the thermometer is placed in the steam. Okay, and at the steam point, at the ice point means at 0 degree Celsius, steam point means 100 degree Celsius. At 100 degree Celsius also it measures the resistance. What is the resistance measured at 100 degree Celsius? 5.23 ohm. Then question is that when the resistance thermometer is placed in hot bath, not steam, not ice, some temperature is there for the hot bath, the thermometer is placed in the hot bath, then the resistance of the platinum wire is, they gave is 5.795 ohm. And this is at what temperature what happen, like this happens. This is our question. Very simple. Okay, firstly in ice the resistance they give. Okay, thermometer resistance in ice they give. Okay, this is ice. And the next steam, at steam point also they give the resistance, that is R100 they give. And at ice point R0 they give. And some hot water, this one, its temperature we don't know. In this also they gave the they kept the thermometer, and now the resistance is also they gave at T degree Celsius 5.795. Based on this, the temperature is how much, at what temperature? Okay, temperature of hot water bath. Okay, its temperature we require to find out. In that also the resistance they give. Okay, it was very simple. RT they give, and R0 they give, R100 they give. Okay, and now we can use the formula, right? This T at what temperature? At 0 degree Celsius, at 100 degree Celsius resistances they give, and they are asking to find out the resistance at T degree Celsius. We have the formula directly. Just now we derived, that is RT minus R0 by R100 minus R0 into, right, 100. I am expecting you to simplify, okay, the values. Okay, you write the values in this 5.795 minus 5.23 by RT minus R0. R0 is 5 by R100 5.23 minus 5 into 100. Okay, and now this is 0.795 by 0.23 into 100. Now you can simplify this and write the answer in comment. You can write this answer in the comment. Okay, thank you for watching my lecture. Till now, if you not subscribe my channel, I am expecting you to subscribe my channel and share to your friends. Thank you.